The Lewisburg Frumkes Center for Writing and Culture at Hunter College presents 10 years of best-selling authors and great thinkers.
Ray Jayawardhana. Well, there's not a lot you can do about it. The trillions of particles going through your body right now, called neutrinos, as Lewis mentioned, luckily they are pathologically shy, so they don't really interact with you, and they cause no harm, so no reason to worry. So Lewis persuaded me to talk about my own research, which has to do with the search for planets beyond our solar system, which is a very exciting area right now. And that was the subject of my previous book, Strange New Worlds. But before we get into today's excitement, let's think back just for a second. 20 years ago, we knew of just one planetary system, our own solar system. And I think all of you are old enough to know that there used to be 9 planets in it, right? Somehow, since then, we astronomers have managed to lose or demote one of those, to the great dismay of lots and lots of people. There were school children writing letters to astronomers calling us heartless or worse. Cartoonists had a field day. There was at least one protest march I know of in New Mexico, where the discoverer of Pluto, Clyde Tombaugh, lived a good chunk of his life. And 4 different state houses in the United States passed unanimous resolutions declaring that Pluto shall remain a planet. What do these astronomers know? This is the one from New Mexico, but you should Google the one from California, which is particularly interesting, if not amusing. It talks about the uncertainty this creates in the sense of cosmic well-being for Californians. In addition to it being an unfunded government mandate, because now you have to change all the school textbooks, and who's going to pay for that? Presumably not the astronomers. The day that the vote to demote Pluto happened in Prague at a meeting of the International Astronomical Union, where there were about 2,500 astronomers, only about 600 of them bothered to show up for the vote. Compared to all these front page news stories everywhere, that evening I was on 3 different primetime newscasts in Toronto. Doesn't happen very often to an astronomer, right? The level of emotional investment in Pluto's planethood was remarkable. While Pluto was getting all this attention and causing all this commotion, in fact, there has been a true revolution in the discovery and understanding of planets beyond the shores of our own solar system over the last 20 years. In fact, this year is the 20th anniversary of the discovery of the first planet orbiting another normal star other than the sun. This revolution came after centuries of speculation, decades of failed attempts. And the reason it took so long, the reason it was so difficult, is quite simple. But now we're in the midst of this revolution. This plot is showing you the number of planets discovered since 1995 till some halfway through last year. What you should get from it is that the rate of discovery is accelerating dramatically. So just last year, there were nearly 800 planets discovered in 1 year. More than, tripling the number of confirmed planets known before. So we're really at the cusp of the activity right now. The reason it's taken so long is rather simple. It's because stars are a hell of a lot brighter than the planets that they harbor around them. So if you were to go to the nearest star and look back at our solar system, you'd see the brightness of the sun totally overwhelming the very, very faint light from the planets. It's like trying to see faint embers next to a bright searchlight from miles away. You wouldn't see the faint embers because the bright searchlight completely overwhelms your vision. The same is true here. So this plot is showing in factors of 10. This is the only sort of sciencey slide I'm going to show you. Factors of 10 And this is different wavelengths going from the ultraviolet to the visible part of the spectrum where our eyes are sensitive, into the infrared, into the radio, just to point out that the sun is almost a billion times, a few 100 million times brighter than even Jupiter, which is the biggest planet in our solar system. So you can get a sense of how challenging this is. Something that's several 100 million times brighter is going to dominate over the faint planets. And that's the reason we can't just turn our telescope at the heavens, at the nearest stars, and out pops little dots around the star. That would be planets. That would be nice, but that's not that easy. So astronomers have had to be a little bit cleverer and have had to come up with other ways of finding these alien worlds. And the technique that worked, that yielded the first results in 1995, was a technique that we colloquially term as the Wobble Method. So we're used to thinking of the planets in our solar system circling the sun sitting in the center, at least since Copernicus, that's our view. But in fact, as the planets circle the sun, they tug on the sun because the planets themselves have gravity, right? So the biggest of the planets in our solar system, the most massive, is Jupiter. So Jupiter's effect is biggest on the sun. And Jupiter takes about 12 years to go around the sun. So that means the sun kind of wobbles in place over the same period. Because sun is still so much more massive than Jupiter, it doesn't do that, but it sort of does this. But with the exact same period, because Jupiter is tugging on the sun as it goes around it in its orbit. So this is the technique that astronomers have used first to detect other planets. The way we measure the wobble of the star, people tried first to measure the wobble of a star on the sky like that. Turned out that those angles are way too tiny to be measured reliably from the ground. In fact, back in the 30s, an astronomer at Swarthmore College in Pennsylvania thought he had detected a couple of planets that way. Turned out the measurements just weren't good enough. But the way we can do this now is to spread the light of a star into the colors of the rainbow, what we call a spectrum. So in the background here, from red to blue, is a spectrum of the sun. So this is spreading sunlight into all the glorious colors of the rainbow. Except astronomers do it a lot better, which means that we see lots and lots of wavelengths spread out. And if you can see, there's kind of a forest of dark lines superimposed on the colors. Those lines are the fingerprints of very specific elements in the sun's atmosphere. So we can see lines from hydrogen in the sun, helium in the sun, calcium, sodium, and they have very specific fingerprints. You can get the exact same fingerprint by measuring hydrogen gas in the lab as you do in the light from the sun. So these lines fall on precisely the same set of wavelengths always, unless the object is moving. So if the sun is moving a little bit away from us, the lines shift a little bit to the red. If the sun is moving just a little bit towards you, the lines shift just a bit to the blue. So this alternate red and blue shift allows you not to measure the full wobble, but this part of the wobble. So we can't see this part of the wobble, but we can see the back and forth of the wobble. So that's the way that two Swiss astronomers in 1995 discovered the very first planet around another normal star, a star kind of like the sun. And they found a planet, not too surprisingly, a big one, about half the mass of Jupiter. But the big surprise was, unlike Jupiter, which took 12 years to go around the sun, this planet whizzed around its star every 3.5 days. So imagine a gigantic ball of gas like Jupiter, except it's not where Jupiter is in our solar system. In this other system, the Jupiter is even closer than Mercury is to the sun. So it's whizzing around. It's completing a year in less than 4 days. So we call this class of planets now hot Jupiters, because they're being blasted by radiation much, much hotter than our Jupiter. And it was a big surprise, because we didn't expect these giant balls of gas to form and to survive so close to their parent stars. And it turned out to be just the first of many, many surprises that have come about in discovering and characterizing planets around other stars. A second technique that has worked beautifully is to see when planets pass in front of their stars every once in a while. What you're looking at here is the sun, and that little dot crossing the face of the sun is planet Mercury. We call it a transit when every once in a while the two inner planets in our solar system, Mercury and Venus, happen to cross in front of the sun as seen from the Earth. So we see these little dots crossing. With other stars, we don't see them like that. We don't see, giant disks of, the giant yellow disks in the sky. But what we can do is to measure the brightness of stars in the night sky very, very precisely, so that every once in a while we might see a dip in the brightness when a planet blocks a little bit of the starlight. A planet about the size of Jupiter blocks about 1% of the starlight. A planet about the size of the Earth would block about 1 part in 10,000. So you can imagine it's a lot easier to find Jupiters than it is to find Earths. And the other thing about this technique, of course, is that if the planet goes around this way, it never goes in front of the star, you'll never see this transit, right? So you're only seeing the subset of planets where the orbits happen to be, by chance, lined up exactly edge on, or almost exactly edge on. But if you monitor thousands of stars a night, you might find dozens, maybe even hundreds of planets this way, planets that you couldn't see any other way. And the beauty of the technique is you don't need very big telescopes. Telescopes that amateur astronomers have in their backyard, as long as they have a nice CCD camera in the back where you can measure the brightnesses very precisely, you could do it. So this is a battery of telescopes, not much bigger than binoculars, frankly, in the Canary Islands that's used to do this kind of science. Here's actual data, and that's the dip. That's the transit of a planet. So this is a technique that's paid off beautifully in the last few years. Now, until now I tried to convey to you how difficult it is to see a planet directly, but in fact, in 2008, we got this image, and we claimed that we've taken a picture of an extrasolar planet, one of the first. How did we do that? There were a couple of things that helped us. One was technology, a technology called adaptive optics, which is basically a way to take the twinkling out of the stars. When you look at the night sky, the reason we have the Hubble Space Telescope is because of the blurry atmosphere that we live under. So when you see the night sky, you see the stars twinkle. That's the starlight the starlight comes through the Earth's atmosphere, and the air roiling about makes the images fuzzy. But we can correct for that by measuring the atmosphere 50 times a second and correcting for it by having a secondary mirror inside the telescope that changes shape through basically nanoelectronics. So you need computing, you need electronics, you need optics, but you can do this in almost real time, keep up with the changing patterns of air in the Earth's atmosphere, so you can get much sharper images than you could otherwise. And that helped. So we used one of the world's biggest telescopes called Gemini on the big island of Hawaii. We used adaptive optics. But the other clever thing we did was to look at young stars. Because when stars are young, their planets are young, those planets actually produce their own heat. They don't just reflect starlight like the Earth does. But especially gas giant planets like Jupiter, when they're very young, they're still contracting. They're still shrinking in size. And that shrinkage means you're converting gravitational energy into heat. So they glow of their own. So the brightness difference between this young star and that massive planet, about 8 times the mass of Jupiter, is more like maybe 10,000 rather than several hundred million, right? So that was the other thing that helped us. Now, how do we know that's a real planet? We were able to take a spectrum of the planet separately, right here, and show that there is water vapor in the atmosphere of that object. That means it's too cool to be a star. And number two, we went back over a couple of years and showed the two things are moving together on the sky to show that they're associated with each other. Because otherwise, what if that is just much farther away in the distance in the background, happened to be lined up just right, so you think it's faint, it must be a planet, you're fooled. It's just a very distant star, right? So we had two independent ways of confirming that it's too cool to be a star and that it's moving together with the star in the sky. But it's still a very unusual beast. It's about 8 times the mass of Jupiter. The distance between these two is about 11 times farther away than the distance between Sun and Neptune. So it's way, way, way out in the outskirts of that planetary system. It's not like a planet that we have in our solar system. It's very different. Now, of course, we got a bit of coverage, including in this Swedish tabloid. Anyone can get written up in the Times, but not many scientists get written up in tabloids. And in true tabloid fashion, my former postdoc, who is Swedish, tells me they hyped it as an Earth-like world with alien life. Hopefully by now you realize that's the furthest thing it could be. It's incredibly different. Now this picture, which also was announced just a couple of months after our announcement in 2008, the first one, and this is a later image, might not look like much to you. It looks kind of messy. It's not very artistic, not very pleasing to the eye, but it in fact is a historic image. This is the first family portrait we have of another planetary system. This was taken also with the adaptive optics, with the Keck and Gemini telescopes. What you're looking at is an attempt to subtract the star from itself in the image so that you could see things around it a little bit better. But you can see the subtraction wasn't perfect because there's a bit of mess left here, right? There's a lot of junk left here, so ignore that. But these dots, you can best see them down here, 1, 2, 3, 4, are 4 gas giant planets that are in the same planetary system. What's remarkable about this one is because the star is relatively nearby, the planets are closer in than the one I showed you before, that over just a few years, starting in about 2006, 2008, 9, 10, and by 2014, we can actually see these planets orbiting around the star. So you can take snapshots every year, and you see the planets moving just a little bit in the arcs of their orbit. Think about that. You can, in real time, go back and see the planets around another star moving. Every few months, every 6 months, every year, you can go back and take a picture, and they move just a little bit. So in this case, we actually have a lot of information. We have information about their orbits, whether they're stable, a lot of interesting data, but also puzzles. How could you get planets that massive forming around this star? Whereas, our solar system does not have anything bigger than Jupiter. Each of these is between 5 to 10 times the mass of Jupiter. So really hefty beasts. Of course, the biggest sort of explosion of discovery in this field came about because NASA launched a telescope called Kepler in 2009, and it operated for 4 good years, during which it stared at a little piece of the sky about the size of my palm at arm's length, this tiny piece of the sky. It stared at it for 4 full years continuously, and every 30 minutes, it took a picture so that we could measure the brightness of some 150,000 stars very, very precisely to about 1 part in 10,000 for full 4 years, every half an hour. What do you think that was about? Remember the 1 in 10,000? So the goal was, by going into space, having better precision, to try to detect Earth-sized planets through the transit technique, right? Because that's the dip in brightness we expect. And boy, did it do that. Here's just a subset of the planetary systems that Kepler produced, just to get a sense of the diversity of worlds and their planetary system architectures. The way that the orbits are laid out, the masses of the planets, quite an incredible range of worlds and world systems. Much greater in diversity than anything we could have imagined until a few years ago. The other thing that Kepler did was, of course, as it was planned to do, to discover planets that are relatively small. So lots of planets that are less than 1.25 times the size of the Earth, these are the ones that are difficult to find. These are the big hot Jupiters. The Jupiters are easy to find through multiple techniques. The little planets are really difficult to find because the dip in brightness is very small, and then trying to confirm them independently is extremely challenging, because most of the stars that Kepler was staring at are too far away, thousands of light years away, that we cannot do the spectroscopy to see the orbital motion, to see the red shifts, the blue shifts, just don't have enough signal. So that means we have to find other ways of eliminating false positives to be sure that you're looking at little planets, perhaps even some worlds that are not too different from our own. And that's, of course, the big question. Are there any of these worlds that might be habitable, that might have the conditions just right for life as we know it? We call these Goldilocks planets, planets that are not too hot, not too cold. And the key thing is water, that water can remain liquid on the surface of these worlds. Now, of course, the planets also have to have a surface, at least the way we think about the Earth, right? If it's a gas ball without a solid surface, I mean, there could be life, but not the way we imagine our counterparts might be, right? You want a rocky planet, ideally, with water on its surface and a sufficient atmosphere to be able to sustain a stable climate, right? So there's a number of these candidates, about a dozen, are about the right size as the Earth that we have now and are located at the right distance from their star. Here's one example of a Earth-sized planet in the Goldilocks zone, but their star is a very different one in this case. It's a red dwarf star rather than a yellow dwarf star like the sun. It's smaller, it's less luminous, but at the right distance, it could indeed sustain a planet with liquid water. So this is obviously an artist's impression of what a habitable Earth twin might look like elsewhere. The other interesting thing I'm going to kind of quickly preview for you is that when you have a planet going in front of the star, with Kepler we can find its existence, we can try to confirm its orbit, but we can't learn a whole lot else. But when we have transiting planets around nearby bright stars, we can actually do a lot more. In fact, we can try to measure molecules in the atmospheres of these worlds. So I'll just very quickly show you one of the ways to do it. I first told you a planet goes in front of a star, it blocks some starlight. That's the simple version. If you think a little bit more, some of that starlight may actually kind of skim through the upper layers of the Earth, of the planet's atmosphere on its way to Hubble or to a telescope on the ground. So what you could do is try to take a spectrum of the star when the planet is in front and when it's not, and take the difference. And any difference might be because molecules in the atmosphere of the planet absorb a little bit of that starlight, skimming through it. And this was actually done already 10 years ago. Astronomers managed to detect the presence of sodium, which is not that interesting as an element, but it was the first detection of sodium in the atmosphere of an alien planet, a very big planet, a Jupiter-like planet. But we can also do many other interesting things. By now, we measured water, we measured methane in a few cases. So we're starting to be able to characterize what these planetary atmospheres are made of. The other thing we could do is that planets that go in front of the star also go behind the star, right? Because they're in this orbit that's aligned this way. When they go, just before they go behind, you could take a picture of the star plus planet, and then just the star, and subtract this from that. Anybody can do that math, right? Astronomers do fairly simple math, at least the observational astronomers. We do, additions and subtractions, and what's left should be the emission from the planet itself. So my former graduate student, who's now a postdoc at MIT, did this for about a dozen alien Jupiters. And we were able to basically measure the day-side temperature of these planets. Now, these are not planets like the Earth. They're very hot, gaseous, big. But it's a way, the idea that we can do remote sensing across hundreds of light years and tell you this is the temperature in the day side of that planet that I can't even see. I find that mind-boggling. It's quite remarkable. It's not a theory, it's not an idea, it's a measurement, it's data, right? So my current student, Lisa Esteves, is working on doing something even more ambitious, which is not just to see the day side, that's the planet going around the star. You can see the full day side just before it goes behind, full day side as it comes on the other side. But can you see the changing phases of the planet, just like the phases of the moon? Because, right here you're looking at the night side, right? Because the planet's right side is facing the star, you're looking at the back side. But just before it goes behind the star over here, you're seeing almost the fully lit day side. So what she's doing is measuring these changing phases, not just the dark side and the bright side, but everything in between as well. So she's taking measurements of the changing brightness of the star plus the planet. But we know how bright the star is. We assume it's stable. I can tell you when it's not exactly stable, how we correct for it. But basically, you can see the primary eclipse, the secondary eclipse. You can see everything in between. What that's telling her is the changing temperatures on different parts of the planet. So our latest paper, which was just accepted a couple of weeks ago, she's reporting for 14 planets. And what we are finding is that the best explanation is that on the night side, there's clouds forming, and we can see evidence that in the morning, as the day goes by, those clouds dissipate. And by the evening, it's very hot because that side of the planet has been facing the star for half of its orbit. So it's very hot. The idea that you can see evidence of clouds disappearing through the course of the day and getting hot by the late afternoon sun, right? This is a world like you cannot take a picture of. It's a world that you're not standing on, right? The idea that we're starting to get to know these alien worlds in some ways, in a very crude ways, not very detailed way. I can't tell you the temperature to plus or minus 2 degrees. I cannot. I can tell you to within a plus or minus maybe 50 degrees, right? So it's pretty crude. But the idea that we are able to already do this is pretty remarkable. So this is the kind of curve she gets. This is actually phases of Venus in our solar system. But this is the kind of measurement she makes of an alien world's changing phases based on the brightness changes. I won't go into a lot of detail except to show you that we're starting to be able to push these techniques to smaller planets because our interest is not measuring these Jupiters, as interesting as they are, but planets that are maybe not much bigger than the Earth, planets we call super-Earths, because they're a little bit bigger than the Earth. Getting to exactly the same size as the Earth is very difficult right now, but maybe 50% bigger than the Earth we can already start to do. So one of my former postdocs, Ernst Demouy, made a measurement of a transit of one of these super-Earths from a ground-based 2.5-meter telescope just in December. The thing that we want to get at is to take measurements at a whole range of wavelengths of planets that are super-Earths with a whole range of telescopes on the ground, in Chile, in space, in Hawaii, in space, to be able to take measurements of their atmospheres to know what the conditions on their surfaces might be, so that we get to a point we can really establish if these worlds are indeed habitable. Do they have the right conditions for life? What we'd like to get to eventually is a spectrum of an alien planet, roughly the same, with similar qualities to the Earth, but that spectrum that would show what we call biosignatures. This is a spectrum of the Earth itself. The way astronomers have taken this is to point at the moon. Have you heard of Earthshine? It's a phenomenon that Leonardo da Vinci talked about. So when the moon is a little crescent, the rest of it is not completely dark because there's reflected Earth light shining back on the moon. So if you take a spectrum of this part of the moon, what you're getting is a global spectrum of the Earth because it's Earth light reflected on the moon. And on that you see oxygen, ozone, water, carbon dioxide, methane, all kinds of interesting molecules. Any one of these doesn't imply life. There's water everywhere in the universe. But if you had multiple of these biosignatures coexisting, it could at least indicate conditions suitable for life. In the case of the Earth, for example, the methane and oxygen would react very quickly and you wouldn't get them coexisting except for the fact that living organisms continuously produce methane. Cow dung, algae, these are the major contributors of methane to the Earth's atmosphere. So if they didn't exist, you wouldn't have those two coexisting. That's what we're looking for. Now the problem is even if you get a beautiful spectrum like this, which will take the next generation of space telescopes, we are not able to do this right now for alien Earth, we still wouldn't know if whether the planet we're looking at is made of green slime or a civilization, because both produce the same set of biosignatures. Unless we happen to point our radio telescope also at that planet and happen to pick up radio waves, signals that are obviously of artificial origin. And this is something I wrote about in the Times, I guess now 4 years ago. The question of how would people react if we were to find the first tentative but compelling evidence of life elsewhere? Would that be a big story? Would that be a 1-week story? And I was arguing that if it was these telltale signs in the faint light in the spectrum of an alien world, for most of us, it wouldn't be a story that changes your life. However, if it were the case that we also detected radio signals, even if we couldn't decode what the message said, as long as we established that there was a messenger at the other end, that it's not a natural process that produced those radio waves, I think that would be hard to ignore. I think that would be dramatic. I think that would make us confront lots and lots of interesting questions. I think even in the other case, even if you only had tentative evidence through biosignatures in spectra, that would still change our mind, but not overnight. I argued that it would be over generations, that it would come to a point that just like what Galileo did, what Darwin did, has changed our perspective of ourselves, this would too. But it probably won't happen overnight. We don't give up our beliefs overnight, almost regardless of how strong the evidence is. That's just who we are as human beings. I hope you've gotten a sense that we're really living through an incredibly exciting time, particularly in the discovery and characterization of other worlds beyond the shores of our solar system. I don't think it's an exaggeration to say that this moment in history is comparable to when Galileo turned his telescope at the heavens for the first time 400 years ago. And in particular, when he pointed at Jupiter, and he could see 4 little dots, the 4 big moons of Jupiter that we still call the Galilean moons. And he could plot their positions night after night and show people not everything in the universe revolved around the Earth, right? It wasn't an idea, it wasn't a theory. Here's what you can see if you're willing to look. I think that's the kind of moment that we're living through, that for the first time, we know with multiple lines of independent evidence of worlds elsewhere, we can measure their properties, we can get a glimpse of their climates. And there are kids now who grow up, when they're asked to write in primary school about another planet, they write about an extrasolar planet, right? I mean, 20 years is long enough that almost a generation is coming through where we've always known that our solar system was just one of many. I mean, we had assumed that, we had speculated about that for centuries, but we didn't know that, and now we do. And I think that is a big change in the way we understand who we are and our place in the universe. Thank you very much.
Thank you, Ray, for a very provocative talk. And now we'll ask you to make it even more provocative by asking Ray some questions. I'm sure many of you, this must have stimulated some questions. The gentleman in green.
I didn't quite follow when you were talking about temperatures
Yes.
of these planets, how you arrived at absolute temperature. I understand more or less how you get a relative temperature depending on how the planet moves and
Yeah.
phases and stuff, but how do you get an absolute?
Very good question. So it is absolute, but it's still relative to the star, right? Because we're measuring always the combination of light of the star and the planet, and then just separately only the star, right? So if you know the temperature of the star, I can tell you relatively by this much the emission dropped when the planet went behind. So that allows us. And the temperature of the star we can measure pretty well because the spectrum of the star is, we can take it to incredibly high signal to noise. So we can tell, for example, based on transitions of particular atoms, what temperatures they need to be. So, measuring temperatures of stars is not that hard. But measuring the temperature of the planet would be relative to the star, because the planet light we have is pretty feeble. Like, we can't get the same level of, detail straight on the planet. But relative to the star, we can. Thanks. Ian? Okay.
A few months ago, the New York Times did some article talking about how we're using radio telescopes and technology to listen
Yeah.
to other solar systems. And there was a lot of controversy displayed in the article as whether you're not just listening,
Yeah.
but
Yeah.
Do you have a perspective on that?
I do. So this is the question of, should you passively listen to if there's anyone else out there, or should you actively broadcast our presence? And it does raise multiple questions. The most, in a way, kind of the interesting and poetic and challenging one is, who speaks for the earth, right? It's not one country or one culture or one language or one music or one, how do you decide what, if you were intending to broadcast, what you would? So in a way, I think, to be honest, the question is a little more interesting from that perspective about who we are and how would we want to be represented right now than the actual messaging. And the reason I say that is that the ability we have to broadcast technically, like, with sufficient power and in enough sufficient directions, that actually takes a lot of power. If you want a signal to, keep going, and since you don't know who you're broadcasting to, you can't quite aim it in a particular direction. Of course, you can, you can do interesting things, like you can aim at a globular cluster where there's lots of old stars and there must be lots of mature planetary systems, so you can do things like that. But we don't have an individual star nearby to broadcast to, right? So it's a little bit challenging to think of how do you narrow down all those options. Now, I don't think, unlike, I know maybe about a year or two ago, Stephen Hawking caused quite a commotion along these lines when he said, why expect aliens to be benevolent? And I personally think that's silly, because if the chances are, just because of statistics, anyone that's able to pick up our signals would be far more advanced than us, right? And statistically, not by 10 years or 100 years, but by thousands, assuming civilizations survive that long, which we don't know, right? With the one, we don't know much. And if so, this idea of sort of somebody wanting our resources or whatever it's an interesting science fiction premise, but it's not very realistic, given the incredible distances involved. If a civilization is capable of traveling even 100 light years, they would have found whatever resources they need, well before they got here, right? Either they have the technology to get here and do something to us, in which case they wouldn't, because they would have already met their needs, or they wouldn't have the technology to do that anyway. So the only other thing that's more maybe realistic to think about is what impact basically would it have on our collective ego, right? Like, if you don't feel small enough now, confronted with, with a civilization where their technology may not be, as I think Arthur C. Clarke wrote a long time ago, indistinguishable from magic from where we are, maybe we would be so blown away just psychologically, not so much physical damage of any sort whatsoever. That's an interesting thing to think about. Like, is that really, likely to happen? Or given the distances involved, it's still so remote. It doesn't really impact your life, and the rate at which you can transfer information is so slow, right? If someone sends something, you wait, even at the speed of light, how long it takes. You can't really have a conversation. You can have sort of a one-way messaging or kind of very, very, very slow conversation over generations. Will it really change the way, will it, the positive ways we think about it, I think I ended that previous Times op-ed by saying, maybe it is the kick in the pants we need to grow up as a species. To realize, because maybe it will, on the positive side, make our petty squabbles really seem petty. But I don't know. That's not really, an astronomer's expertise. It's more about human behavior and psychology and sort of social psychology. It's hard to predict, but it will be, I think, incredibly interesting regardless. My own sense is things won't change overnight. The idea that, only a very small fraction of people change strongly held beliefs no matter what, right? So it will take, but new generations will grow up with a very different perspective, given this evidence that doesn't add up, and they will have a very different way of dealing with it. So it's a bit of a windy answer, but it has so many interesting, I think it's an incredibly interesting thing to think about, whether it's a real, urgent, practical issue. Yeah, I'm less convinced.
1 minute, I wanted to ask myself a silly question. when we were coming up in the elevator, I was half serious and kidding with you, and I said, I think we are the last generation of human beings as we know ourselves, because within 50 years we'll all have chips in our heads and be cyborgs and virtual partners and everything else. That's in 50 years. Whether that is accurate or silly, it's not important. You were just talking about beings that might be 1,000 years ahead of us. Would they be beings anymore? Would they be machines or air? I mean, what would some civilization of that level of intelligence and technology resemble?
Yeah, it's an excellent question, which also sort of definitely challenges one of the premises of our search for life, right? If incredibly advanced technological life is, computers, well, they're not going to be producing methane, right? I mean, should we be looking for methane as a biosignature at all, right? So it is a very interesting question, which is very, very difficult to, at least from a scientific perspective, to work through, because the fundamental challenge is when you have one example of life, you cannot generalize. And if there's one message you can take from the story of the exosolar planet discovery, is that when we had the one planetary system, we had no clue of the range of diversity of planetary systems that are possible out there. Because you cannot do that. Like, how do you generalize from one example, right? So one of the things that's happened, this is kind of moving away a little bit from your question directly, but one thing that's happened is, for example, why are there no hot Jupiters in our solar system? And our idea is that hot Jupiters elsewhere formed further away from their star and migrated inwards and parked themselves in these very tight orbits. Well, did planets move around in our solar system? And now we know they did. But we didn't know that before. It's only when we saw the big migrations elsewhere that we looked back at our own solar system architecture and realized, actually, Jupiter probably moved in a little bit. And the latest papers suggest that during that motion inward of Jupiter, there might have been other planets in the inner solar system that fell into the sun. That Mercury might be the last of the Mohicans that didn't fall, right? And then we know in the outer solar system, there was also outward migration of Uranus and Neptune. We see the dynamical signatures of that in the Kuiper belt, which is the kind of like the asteroid belt. There's a collection of small bodies well beyond the, Pluto is considered to be part of it, beyond the orbit of Pluto. And we can see gaps in that, belt that suggest evidence of migration in the past. So how come we didn't recognize that before? Part of it is because those are much more subtle movements compared to what we've seen elsewhere in other planetary systems. But seeing that perspective, all of a sudden we recognize. And I think the biggest change when we discover life elsewhere will be not in astronomy, but in biology. Like, how do you define life? If you had two examples, you can start to say, okay, these two are incredibly different, but do they have anything in common? And that common thing or things may be the way we define life. If it has this, this, and this, because both of them have that, that would be how you define life. And then when you have a third example, you may have to revise your definition again, right? But at some point, you'll have a much better sense of what is universal versus what is particular. And I think, unfortunately, the real answer to your question is we don't know till we know, right? Jacqueline? Yeah.
I would like to ask you if the activities that we exercise on Earth, like, for example, nuclear weapons and chemical weapons and, very dangerous things that we do here on Earth, is there any way to measure whether they affect the atmosphere and how they affect the atmosphere? And does it come back on us, after we put it out there? And does it affect any other planets or anything like that?
Okay. So when you have nuclear explosions in the atmosphere of the Earth, indeed it affects the atmosphere of the Earth. But anything we do, any technology we have still, it's enough to destroy ourselves, but it's not enough to destroy another planet even in our solar system. And the sun is certainly not, even if you throw all your nuclear weapons at the sun, nothing is going to happen. It's because it's a much more powerful nuclear bomb, in some sense, an ongoing bomb set of explosions, than anything we can even remotely, achieve, right? But it does have impact on Earth. For example, I mean, the whole, it is not considered as big a danger these days because of the geopolitical situation. But at some point, people did worry about what Carl Sagan called nuclear winter, right? If you have a true large-scale nuclear war on Earth, you would kick up enough particle matter into the atmosphere that you would basically block out sunlight for a while, which means that, it'll affect climate, it'll affect the food cycle, vegetation, all of the, all the food chain completely, not just for humans, but for other animals. So for sure, but we don't, hopefully, we don't no longer feel like we're living under that level of nuclear threat, partly because of mostly because of the geopolitics have changed so much. That doesn't mean there couldn't be, small nuclear wars on Earth, but not at a scale that would change, all life on Earth unless, the major powers decided to go at it. But
Are there any more questions? We'll take one more question, and then we'll move to the rear of the room where Ray will sign books, and you may all have coffee and refreshments. The gentleman in brown jacket.
There's a recent article in Science News about rogue planets. And it mentioned what you said about Jupiter moving in and out and possibly even ejecting a planet that's no longer in the solar system instead of sending it to the sun. And so far they found about 40 of these rogue planets, basically planets that don't have any stars.
yeah.
But there might be really a lot of them because they figure it might happen in most star systems.
Yeah.
So these things that are planetary systems.
Sure.
In that case, when we think of something like interstellar travel to Alpha Centauri,
Yeah.
it's more like we didn't think of it as we got to get there in one jump.
Yeah.
They're going to be that common, maybe when we start to think of any steps along the rogue planets.
Well, so the rogue planets, it's an interesting idea. It's something I do research on, so I know something about it. So the what we call, colloquially call rogue planets are basically planets that don't circle stars, right? But one of the questions that we are researching is, all the ones we know about, first of all, that we measured are more like Jupiter. They're big, or bigger than Jupiter, right? So the question is whether they even formed like planets in a planetary system and got ejected, which is quite possible because of all these migrations early in the history of the planetary system. But it's also possible that they form just like stars do through the collapse of a small cloud of gas and dust. So they could be sort of the failed stars. The bottom end of the range of stellar masses could be, too little that you would call it a planet in terms of its mass, even though it formed like a star, right? So there could be lots of them. There could also be Earth-sized planets out there. But the problem is that, without a star, they cool down over time, so there's no source of energy. That's the problem. So how do you sustain life? It's hard to imagine using them as spacecraft or base stations because they wouldn't give you, they might give you, silicon, but they won't give you, heat. They won't give you energy. So it is, in principle possible that there's free-floating planets between us and Alpha Centauri, but probably less so. The other thing I just want to end with this idea that I think one of the things that's really exciting about this area of research is that it's pure science. I don't do it because I'm going to make a better toaster for you or a better, cell phone for you. But it does lead to those things, right? Astronomers developed CCDs, which are in your, smartphones now, right? We do that, but what I think is incredible about it is that it's really has the potential to change who we are in a more fundamental way. Like in terms of, why, what are we doing here? Like what can be more inspiring than sort of being driven by our curiosity and figuring out what's out there. And the fact that we can do it at all, I think is pretty remarkable. And it is technology, but it's really, at the end of the day, it's human ingenuity, right? That produced the technology that enabled us to do things. And to think of new ways of asking and answering the questions. So I feel very privileged that, I get up thinking, how do I, think of a question and think, how do I figure out an answer? And it's very uplifting. It's very inspiring. And I hope that, not everybody especially the kids who, think about astronomy don't end up all be astronomers, which is a good thing because we don't have enough jobs for all of them. But they do go on to do interesting things with their lives because they were inspired by this sort of very grand ideas and grand sort of themes that are basic questions of who we are, where did we come from, what's the universe about, that every kid thinks about at some point. Some of them stick with it. They don't want to grow up, and others grow up, but still, at least, that may affect choices you make. So thank you very much, and thank you to Louis.
Ray, thank you for a very stimulating and provocative talk. I hope you all enjoyed it, and I hope you'll come back and say hello to Ray and perhaps get a book that he could inscribe for you and have some coffee and refreshments. Thank you, Ray.
Thanks.